Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So if you look at the absolute oldest light in the universe, the grand cosmic math says reality is 13.8 billion years old.
Right.
But, and this is where it gets crazy, if you look out your cosmic window right now at the stars and galaxies relatively close to us, the local math insists the universe is a billion years younger.
Yeah, it's a massive discrepancy.
Like, let that sink in for a second. We haven't just misplaced, your car keys. We have somehow misplaced an entire billion-year era of cosmic history.
And losing a billion years, that isn't a mere rounding error. It fundamentally shatters our entire timeline.
Yeah.
It throws into question, really, our understanding of how galaxies assembled when the first stars ignited, and even how the very fabric of space and time behaves on a macroscopic scale. We are dealing with highly precise data sets here, and they are pointing in two completely contradictory directions.
It is a massive crisis in modern astronomy. They often refer to it as the Hubble tension. So for everyone listening, our mission today is to break down a really fascinating new approach to solving this exact standoff. There's this massive research effort led by Indranil Banik at the University of Portsmouth, and they submitted a study this past July that tries to finally settle the debate.
Which is incredibly exciting.
Right. But instead of peering out to the very edge of the observable universe, they are looking inward. They're hunting for the absolute oldest, most pristine cosmic fossils, right here in our own galactic backyard, the Milky Way. So we are going to explore these two conflicting tape measures of the cosmos, break down how a staggeringly massive census of over 155,000 ancient stars is acting as a tiebreaker, and explore the incredibly wild possibility that our local neighborhood of space might just be completely distorting our view of reality.
The shift in methodology here is crucial to understand because for decades, cosmology has relied really heavily on measuring the stretching of space itself. Exactly, the container. This new approach entirely abandons the attempt to measure the container, so to speak, and instead focuses on finding the oldest possible objects sitting inside that container.
But let's start with the container, though, because I feel like you need to understand the standoff before you can appreciate the solution. The core of this crisis revolves around measuring how fast the universe is expanding, which is a metric known as the Hubble constant.
Right.
And the tension exists because we have this 9% mismatch between two historically bulletproof methods of measuring that expansion. Let's talk about tape measure number one, the early universe.
So the early universe method relies on something called the cosmic microwave background, or the CMB. To picture this, you have to imagine the universe about 380,000 years after the Big Bang.
Okay, pretty early on.
Very early. Before this point, the universe was so intensely hot and dense that it was essentially a thick fog of plasma. Photons of light couldn't travel freely. They just, constantly smash into free electrons.
So the universe was effectively opaque, right? Just a giant, glowing, superheated cloud where light was totally trapped.
Precisely. But as space expanded, it naturally cooled. And right around that 380,000 year mark, the temperature dropped just enough for electrons to finally bind to protons, which formed the first neutral hydrogen atoms.
And that's when the fog lifted.
The fog lifted. Light could suddenly travel unimpeded. And that first burst of free light has literally been traveling through space for billions of years. As the universe has expanded, those ancient light waves have been stretched out into the microwave spectrum.
So when we point spiralized radio telescopes at the sky today, we could actually see the afterglow of this exact event.
Exactly.
It's like we're looking at a baby picture of the universe.
We are. And that baby picture, interestingly, is not perfectly uniform. It has microscopic temperature fluctuations, these tiny hot and cold spots. By analyzing the physical size and distribution of those temperature ripples, cosmologists can apply our standard model of the universe.
Which is known as the lambda CDM model. Hold on, let's not let that acronym just slide by. Lambda CDM. What physically are we talking about there? Because I know that model is doing a whole lot of heavy lifting in this measurement.
Sure. So lambda represents dark energy. This is the mysterious intrinsic energy of space itself that is causing the expansion of the universe to accelerate.
It pushes things apart.
Yes, it acts like a repulsive gravity, pushing space apart. Then CDM stands for cold dark matter. This is the invisible, slow-moving matter that doesn't interact with light at all, but it exerts a massive gravitational pull. It acts as the invisible scaffolding for galaxies.
So we basically have dark energy pushing everything apart on one side and cold dark matter trying to pull it all together on the other.
Exactly. The lambda CDM model perfectly balances those two opposing forces. By plugging the temperature fluctuations of the CMB baby picture into this mathematical model, cosmologists can calculate exactly how fast the universe was expanding in its earliest moments.
Yeah.
And then they can project that math forward to the present day. When you run that simulation all the way to its conclusion, the math dictates that the universe has been expanding for 13.8 billion years.
Okay, so that is tape measure number 1, giving us a universe that is 13.8 billion years old. It is an incredibly sophisticated deduction based on the oldest light in existence. But then we have tape measure number 2. And this one doesn't look at ancient, stretched-out microwaves. It looks at the local present-day universe right outside our cosmic front door.
Right. The local measurements rely on a completely different astrophysical tool. They use standard candles.
Standard candles.
Specifically, astronomers look at pulsating stars called Cepheids and exploding stars known as type Ia supernovae. The fundamental principle of a standard candle is that we know its exact, intrinsic, true brightness.
Let me make sure I'm wrapping my head around this. If I look out my window at night and I see a dim street lamp, it might be, a tiny flashlight 100 feet away, or it could be a massive stadium floodlight a mile away.
Exactly.
Without knowing its true brightness, I can't determine its distance at all.
That is the fundamental problem of all astronomical observation. You can't just take a literal tape measure to the stars. But standard candles solve this. Back in the early 20th century, astronomer Henrietta Swan-Leavitt discovered that Cepheid variable stars pulse at a rate that is directly tied to their true brightness.
So they basically blink.
Yes. And a slower pulse means a brighter star. Once you measure the pulse rate, you know exactly how bright the star truly is at its source.
So going back to my street lamp analogy, the star essentially tells you, hey, I am exactly as bright as a 100-watt bulb. So when you look at it in the telescope and it looks incredibly dim, you can use a simple inverse square law of light to calculate precisely how far away it must be to appear that dim to us.
You've got the distance, that's half the puzzle. Now you need the speed, because the Hubble constant is all about distance and speed. To get the speed, astronomers measure the redshift of that star's light. Yeah. As the star moves away from us due to the expansion of space, the light waves it emits get stretched out over that distance. The wavelength becomes longer, shifting toward the red end of the light spectrum.
Oh, it's like the visual version of the Doppler effect. Like when an ambulance speeds away from you, the sound waves stretch out and the pitch drops. In space, as a galaxy speeds away, the light waves stretch out and the color reddens.
That's a perfect analogy. So by combining the precise distance from the standard candle with the precise speed from the redshift, astronomers can calculate the local expansion rate of the universe today. And here is where the crisis erupts.
The tension.
The local measurement reveals a noticeably higher expansion rate than the early universe CMB measurement predicts.
The universe right around us appears to be flying apart roughly 9% faster than the early universe baby picture said it should be. And that brings us to the mathematical nightmare here. If space has been expanding at this faster rate for almost all of cosmic history, it wouldn't have taken 13.8 billion years to reach its current size.
Not at all. It would have reached its current volume much, much faster. If you apply the local expansion rate retroactively, the universe is suddenly only 12.5 to roughly 12.9 billion years old.
13.8 billion on one side, 12.5 billion on the other. That is a gap of over 1 billion years. Now, I have to ask the obvious question that anyone listening is probably, shouting at their speakers right now. Why can't we just split the difference? Why not just average the two numbers, say the universe is, 13.2 billion years old, and call it a day?
Splitting the difference is intellectually dishonest in physics. It is equivalent to taking a thermometer that says water boils at 100 degrees and another that says it boils at 90 degrees and just deciding water boils at 95 degrees.
Right. It doesn't work that way.
No, these aren't sloppy approximations. The instruments measuring the CMB, like the Planck satellite, are total marvels of engineering. The telescopes observing the Cepheids, like the Hubble Space Telescope, have been calibrated relentlessly for decades. The 9% discrepancy is significantly larger than the combined margin of error for both methods.
So we absolutely cannot chalk this up to, like, a smudge on a telescope lens or a bad line of code in the software. A 9% discrepancy on a cosmic scale means there has to be a physical reason for the mismatch, which leaves us with two pretty terrifying possibilities.
Yeah.
First, there could be some entirely new physics, some exotic energy field or particle behavior that shaped the universe's expansion from its earliest moments that our lambda CDM model is completely blind to. Or, conversely, this fast local expansion rate is an illusion created by something weird in our local neighborhood.
The scientific community has been at a total impasse over this. Are we missing a fundamental piece of the cosmological puzzle, or is our tape measure skewed by where we live? And to break a deadlock like this, you cannot keep using the same tools. You can't just run another CMB scan or catalog another 1,000 supernovae.
You need a totally independent referee. Which brings us to Indra Nobanek and the University of Portsmouth team. They realize that you have to stop measuring the stretching of the container. If you want to know how old a house is, you don't necessarily measure how far the wooden beams have warped over time.
Right.
You look for a newspaper stuffed in the walls during construction. You date the objects inside the space.
This relies on what is formally called the minimum age principle. And the logic is as robust as it is simple. The universe cannot possibly be younger than the oldest object within it.
I love this concept. It's like paleontology, but for the cosmos. If a geologist is trying to determine the age of a rock formation, they look for fossils. If they dig into a canyon wall and find a trilobite fossil that carbon and radiometric dating proves is, say, 500 million years old, then they know for an absolute undeniable fact that the canyon rock must be at least 500 million years old.
Exactly.
The rock cannot be younger than the fossil trapped inside it.
Stars act as these exact cosmic fossils. If you can accurately isolate and date the absolute oldest star in our galaxy, you establish a hard physical floor for the age of the universe. Of course, you have to add a small buffer of time to account for how long it took that star to physically form after the Big Bang, but it gives you a definitive baseline.
And this methodology is a direct attack on the younger 12.5 billion year estimate, right? If the local expansion rate is correct and the universe is only 12.5 billion years old, then it should be physically impossible to find a star that is 13 billion years old. Finding a 13 billion-year-old star would immediately bust the local expansion theory, at least as a universal constant rule for all of space.
The theory is flawless. The challenge is the execution. The Milky Way contains anywhere from 100 to 400 billion stars. You are searching for the absolute oldest members of a population that vast. You cannot merely point a telescope and estimate the age of a star just by looking at its color or size on the main sequence.
The main sequence being the long, stable middle age of a star's life, right? Like what our sun is doing right now.
Yes. For the vast majority of its existence, a star is in hydrostatic equilibrium. Gravity is constantly trying to crush the star inward, but the immense heat and pressure from nuclear fusion in the core, where it's fusing hydrogen into helium, creates an outward pressure.
It pushes back.
Exactly. As long as the star has hydrogen to burn, those forces are perfectly balanced. It remains stable, its brightness barely changes, and its temperature remains relatively constant for billions of years.
So if I'm trying to find a star's exact age, looking at it during this phase is basically useless. It's like trying to tell the difference between a 30-year-old human and a 35-year-old human just by looking at them sitting on a couch. The physical changes over that 5-year span are too subtle to measure accurately.
That's a great way to put it. To accurately date a star, you need to catch it at a moment of extreme structural transition. And this brings us to the specific focus of Banach's team, a very precise evolutionary stage known as the subgiant phase.
Okay, walk us through the astrophysics of a subgiant. Why do we care about this specific kind of awkward teenage transition phase of a star? What is physically happening inside the star that makes it a perfect clock?
A star enters the subgiant phase the very moment it exhausts the hydrogen fuel in its core. The fusion engine at the very center just shuts down. Because that outward thermal pressure disappears, gravity instantly starts winning the battle.
Oh, wow.
Yeah, the helium core begins to collapse in on itself under its own weight.
That sounds catastrophic for the star.
It is a massive physical crisis. As the core collapses inward, the extreme compression generates an immense amount of new heat. This heat radiates outward and actually ignites a fresh shell of unfused hydrogen that surrounds the dead core. So now you have fusion happening in a shell around the core rather than right in the center.
That's burning.
Yes, shell burning. And the energy generated by this new shell burning is so intense that it forces the outer gaseous layers of the star to rapidly expand and cool. The star begins to balloon in size. It has left the stable main sequence and is well on its way to becoming a massive red giant. The subgiant phase is that incredibly brief volatile window caught right in between.
But wait, I'm confused here. You're telling me a star going through a massive structural crisis, its core is collapsing, a new shell of fire igniting, its outer layers ballooning out of control that makes it easier to date. If I'm trying to figure out how old a car is, I don't photograph it while the engine block is actively exploding. Doesn't that volatility make it a terrible clock?
It's a completely fair question, but the instability is exactly the feature we need. Because the star's structure is changing so rapidly during this phase, its surface temperature and its overall luminosity, its true brightness, change dramatically over a relatively short period of cosmic time.
Ah, I see. It's moving fast on the graph.
Exactly. When a star is on the stable main sequence, its brightness changes at a glacial pace. But during the subgiant phase, the luminosity becomes hypersensitive to the star's precise mass and its age. By mapping the exact surface temperature and the exact luminosity of a subgiant, astrophysicists can run stellar evolution models backward with incredible precision. The rapid physical changes give us a much tighter temporal window.
Okay, so subgiants are the perfect cosmic clocks because they're in the middle of a highly visible, mathematically predictable growth spurt. Now we need the data. And you can't just comb through a few hundred stars. To find the absolute oldest fossils, the researchers pulled data from two of the most monumental astronomical surveys ever conducted, Gaia and Lamast.
These two surveys provide complementary data sets that are fundamentally altering our understanding of the galaxy. Let's start with Gaia. The Gaia Space Observatory is engaged in the most ambitious astrometry mission in human history. It is precisely measuring the positions, distances, and proper motions of over 1 billion stars.
Astrometry is essentially the 3D mapping of the galaxy, right?
Yeah.
But how does it actually know how far away a star is without using those standard candles we talked about earlier?
Gaia uses a geometric principle called parallax. As the Earth orbits the Sun, our vantage point in space shifts by about 186 million miles from one side of the orbit to the other.
Oh, like if you hold your thumb up in front of your face and close your left eye, then open it and close your right eye, your thumb appears to jump back and forth against the background of the wall. That's parallax.
Precisely. Gaia takes incredibly precise measurements of a star's position against the background of distant, unmoving galaxies. 6 months later, it takes the measurement again from the other side of the solar system. By measuring that tiny apparent shift, which is microscopically small, equivalent to measuring the width of a human hair from miles away, Gaia can calculate the exact distance to the star using simple trigonometry.
So Gaia gives us the perfect 3D position and distance. What does LAMOS do? That's the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. A total mouthful of an acronym.
LAMOS provides spectroscopy. If Gaia is the map, LAMOS is the chemical laboratory. A spectroscope takes the light emitted from a star and splits it into its component colors, like a highly advanced prism. But when you look at that resulting rainbow, there are tiny dark lines missing from the spectrum.
The absorption lines.
Yes. Different chemical elements in the star's atmosphere absorb very specific wavelengths of light. By looking at which specific lines of color are missing, astronomers get a literal chemical barcode. LAMOS reads that barcode to tell us exactly what elements a star is made of.
Which is absolutely crucial for dating a star. I want to really dig into this because how does reading a chemical barcode of a star actually tell you how old it is?
This involves the concept of metallicity, and it requires a really quick history of the elemental universe. In the immediate aftermath of the Big Bang, during the first few 100 million years, the universe consisted almost entirely of hydrogen and helium, with just trace amounts of lithium. That was it.
The periodic table was basically just 2 blocks.
Correct. So the very first generation of stars, which astronomers call population third stars, were forged purely out of this pristine hydrogen and helium gas. Inside the extreme pressure of their cores, these massive early stars fused those basic elements into heavier elements: carbon, oxygen, nitrogen, all the way up to iron.
And when astronomers say metals, they don't just mean iron or gold. In astrophysics, anything heavier than helium is lazily referred to as a metal, right?
A charming quirk of astronomical jargon, yes. Oxygen, carbon, neon, astronomers consider them all metals. Now, when those massive first-generation stars died in spectacular supernova explosions, they violently scattered all those newly forged heavy metals out into the surrounding interstellar gas clouds.
So they seeded the universe with the heavy stuff.
Exactly. The next generation of stars, population 2 stars, formed from those seeded gas clouds, so they incorporated a small amount of those heavier metals into their structure. They lived, they died, they exploded, seeding the universe with even more metals. Finally, you get to population I stars, like our own sun, which formed relatively recently from heavily enriched gas. Our sun has a high metallicity because it is essentially made from the recycled polluted guts of multiple dead star generations.
This is an incredible detective story. So if you are hunting for an ancient cosmic fossil, you do not want a star with a lot of carbon or iron. You want a star that is fundamentally devoid of heavy metals, because that proves it formed back when the universe was incredibly young and chemically pure.
A true ancient fossil will have an exceedingly low metallicity. By utilizing Lamost's chemical barcodes, Bannock's team could filter their massive data set. They started with 247,103 subgiant stars identified by Gaia and Lamost, but they needed to brutally sift through this catalog to ensure absolute purity.
They executed a massive purge of the data. They systematically removed any star whose chemical barcode didn't perfectly match the expected low metallicity signature of an ancient star. But they didn't just stop at chemistry, did they? They applied multiple layers of quality cuts.
They did. They removed stars that had anomalous velocity readings, stars where the parallax data from Gaia had a high margin of error, and stars that might be part of binary systems where gravitational interactions could completely skew the luminosity readings. They even ran cross-checks using completely independent statistical methods to verify the integrity of the data points.
By the end of this grueling filtration process, that initial massive haul of 247,103 stars was brutally whittled down to a final verified sample of 155,600 stars. I just want to pause and appreciate the immense rigor of that. They intentionally threw out nearly 100,000 perfectly good data points, simply because those points had a tiny fraction of a percent of uncertainty attached to them.
Right, they had to be certain.
They sacrificed enormous raw quantity to guarantee that the remaining 155,600 stars were structurally, chemically, and physically bulletproof.
It is a true masterclass in data hygiene. When your conclusion threatens to rewrite the fundamental age of the cosmos, your foundation cannot have a single crack in it.
So the foundation is set. We have 155,600 meticulously verified subgiant stars functioning as hyper-accurate cosmic clocks, all guaranteed to be low metallicity fossils from the dawn of time. The team analyzes the exact luminosity, surface temperature, and chemical composition of every single one. What time do the clocks actually say it is?
After running the stellar evolution models backward on this pristine sample, the team reached a highly definitive conclusion. The oldest long-lived star in the Milky Way galaxy based on this vast census is approximately 13.73 billion years old.
13.73 billion years old. That number alone feels like a massive victory for the early universe tape measure. But before we just declare a winner, how tight is the margin of error on that number? Is it 13.73 billion, give or take a billion years?
The precision is what makes the study so compelling. The calculated age comes with an incredibly tight uncertainty window. Roughly plus 0.18 or minus 0.15 billion years.
That's nothing.
We are talking about a margin of error of barely over 100 million years on a timescale of nearly 14 billion.
Okay, so the oldest star in the Milky Way is definitively 13.73 billion years old. But, looping back to the minimum age principle we discussed earlier, the oldest star is not the exact age of the universe itself. The universe had to exist for some amount of time before this star could physically form.
This is a critical cosmological phase known as the Dark Ages. When the Big Bang occurred, space expanded and the plasma cooled, which gave us the cosmic microwave background, but the universe was completely devoid of stars. It was a vast, pitch-black expanse filled almost entirely with neutral hydrogen gas.
Just dark clouds of gas expanding into nothingness. How long did it take for gravity to actually do something with that gas?
It takes an immense amount of time for gravity to overcome the kinetic energy of the expanding gas. Gravity has to slowly pull microscopic clumps of hydrogen together. The clumps gain mass, their gravitational pull increases, they draw in more gas, the pressure builds, the core temperature rises to millions of degrees, until finally the density is so extreme that nuclear fusion ignites.
The first light turns on. How long does our standard model say that process took from the moment of the Big Bang?
Based on the physics of gas dynamics and gravitational collapse, specifically calculating what's called the gene's mass, the most robust cosmological models assume this dark age period lasted roughly 200 million years, or 0.2 billion years.
All right, let's do the final arithmetic. We take the definitive age of our oldest subgiant fossil, 13.73 billion years. We add the 200 million years of the dark ages required for that star's hydrogen gas to coalesce and ignite. 13.73 plus 0.2 gives us roughly 13.9 billion years.
Which represents a monumental validation of the standard lambda CDM model. 13.9 billion years aligns almost perfectly with the 13.8 billion year age predicted by analyzing the cosmic microwave background.
It is stunning. The container is 13.8 billion years old, and we know this because the ancient subgiant fossil sitting right here in our own galaxy demands a timeline of nearly 13.8 billion years to exist. This completely decimates the local expansion theory as a universal baseline, doesn't it?
Oh, absolutely.
Like, if the local measurements of Cepheids and supernovae were universally true, and the universe was only 12.5 billion years old, these subgiant stars simply could not exist. They would be older than time itself, which breaks every law of causality.
It reinforces the early universe measurements profoundly. The team also noted that this 13.9 billion year figure perfectly aligns with prior independent studies that attempted to date globular clusters, which are incredibly dense, spherical collections of millions of very old stars orbiting the galactic core, multiple independent physical phenomena, the ancient microwave afterglow, the dating of globular clusters, and now the precise stellar modeling of 155,000 subgiants are all converging on the exact same chronological baseline.
Okay, as much as I want to celebrate this perfectly neat conclusion, true scientific rigor isn't about slapping a bow on a result and walking away. We have to violently poke holes in this. If I'm a skeptic advocating for the younger 12.5 billion year universe, how do I attack this 13.73 billion year stellar age? The research team must have published their own uncertainties.
They absolutely did. Transparency regarding the limits of measurement is the hallmark of robust science. The team explicitly codified 5 specific sources of potential error, 5 pillars of uncertainty that could systematically shift their final calculation.
Let's put these pillars on trial. I really want to challenge them. Number 1 on their list is sample size. Now, they started with 247,000 stars and whittled it down to 155,600. That is a massive data set. Why is sample size still a massive pillar of uncertainty?
Because the Milky Way galaxy contains up to 400 billion stars. Even a pristine sample of 155,000 stars is a microscopic fraction of the total population. The statistical reality is that they may have simply missed an older outlier. Perhaps the true oldest star is sitting in a quadrant of the galaxy heavily obscured by interstellar dust, completely invisible to the Gaia and Lamos sensors.
So the true age could theoretically be even older, pushing the 13.73 number higher. What about pillar number 2, quality cuts? This refers to the great sifting. We talk about removing the high metallicity stars and the binary systems. How does making the data cleaner introduce uncertainty?
Because every time you define a parameter to cut data, you are imposing a human-made threshold on nature. For instance, determining the exact cutoff point for what constitutes low metallicity is a theoretical decision. If they set that threshold slightly too high or slightly too low, they could accidentally exclude older stars or falsely include younger stars, skewing the overall age distribution.
I see. The scalpel might have been a millimeter off. Moving to the third uncertainty. Stellar model assumptions. This one seems like a huge vulnerability. We're relying entirely on complex computer simulations of how the cores of subgiant stars collapse and ignite hydrogen shells. What if our fundamental understanding of subgiant astrophysics is just flawed? What if the fusion mechanics operate slightly differently under extreme low metallicity conditions?
It is a very valid critique. If our thermodynamic equations modeling the core collapse phase have a blind spot, then our physical clock is inherently biased. The star might be ticking through its subgiant phase 5% faster or slower than our algorithms assume.
Which would throw off the entire age calculation. Okay, 4th on their list, star formation timescales. This targets that 200 million year buffer we added for the dark ages. Let me push back on this. We assumed it took 200 million years for the first gas clouds to ignite. But what if the early universe was vastly denser than we think, and gravity worked much faster? What if the population thirst stars formed in just 50 million years?
The time frame of early star formation is highly debated because we cannot directly observe the first generation of stars. We can only model their formation via fluid dynamics and dark matter clustering theories. If the first stars ignited much faster, say in 50 million years, it reduces the total age of the universe. Conversely, if it took 400 million years for gravity to overcome the kinetic energy of the early plasma, the universe must be older.
And the final pillar of uncertainty, theoretical predictions. This feels a bit like a catch-all safety net.
It acknowledges the overarching reality that our macroscopic cosmological frameworks, including the lambda CDM model itself, are merely mathematical approximations of reality. They are not reality itself.
Okay, so they've listed these 5 major vulnerabilities. From a skeptic's point of view, it sounds like this study is built on a very shaky foundation of assumptions.
Here is where the brilliance of their self-analysis comes into play. The team mathematically quantified the impact of each of these uncertainties. They calculated that every single one of these 5 factors limits the overall precision by roughly 0.15 to 0.2 gigayears, meaning a flaw in any one of these pillars only shifts the final age by about 150 to 200 million years.
Oh, that completely flips the narrative. That means their methodology is incredibly robust. It's not relying on one massive, fragile assumption. It's balancing several small, highly constrained variables.
Precisely. They noted that because the uncertainties are distributed evenly across these 5 factors, no single magical improvement in observation technology or theoretical physics would sharply refine the result overnight.
And here is the fatal blow to the local expansion theory. Even if you stack all 5 of these uncertainties against the 13.8 billion year model, even if you push every single margin of error to its absolute maximum limit to force a younger calculation, the estimated age of the universe still lands notably higher than 12.9 billion years. The absolute floor of reality holds firm.
The universe simply cannot be 12.5 billion years old if it contains a massive, statistically unassailable population of subgiant stars whose physical structures demand they are at least 13.5 billion years old. The astrophysics of the stars forbid it.
The early universe tape measure was right. The universe is about 13.8 billion years old. But this leaves us with a galaxy-sized elephant in the room. If the universe is definitively 13.8 billion years old and the lambda CDM model is fundamentally correct about the early universe, why on earth do our local measurements of Cepheids and supernovae insist that the space right around us is expanding 9% faster? What is actually causing the Hubble tension?
This is where the implications of Banach's stellar census force us into incredibly bizarre territory. Because this study mathematically demands an older universe, it allows us to completely rule out an entire category of theoretical physics. For years, theorists proposed that the Hubble tension was caused by early universe new physics. They suggested some exotic, undiscovered energy field was present immediately after the Big Bang, altering the initial expansion rate universally.
But because these ancient stars exist, we know the early universe must have behaved exactly as the lambda CDM model predicted. If weird new physics was universally accelerating expansion from day one, the universe would have reached its current size far too quickly, the timeline would be compressed, and those 13.7 billion-year-old subgiants just wouldn't have had time to form.
Exactly. The existence of the fossils proves the early climate was stable. So the research team pivots entirely. If the early universe was behaving normally, they favor what is called a late universe solution.
Meaning the rules of the game changed recently.
It posits that whatever fundamental mechanism is causing the Hubble tension, it is a relatively recent phenomenon in cosmic history. The universal rate of expansion hasn't been a smooth constant. Something has actively altered it, perhaps only within the last few billion years.
The idea that the very fabric of space and time is behaving differently today than it did for the first 10 billion years of its existence is profoundly unsettling. But the researchers didn't stop at a late-time universal shift. They proposed a wildly different structural alternative. And frankly, this hypothesis is even more staggering. They suggest the Hubble tension might be a purely local illusion caused by a massive local underdensity.
The void hypothesis.
Yes. Okay, let's build a visual for this. Imagine you are driving on a massive, densely packed superhighway. You are completely boxed in by thousands of heavy semi-trucks and cars. The combined mass and traffic flow force everyone to move at a grinding, steady 55 miles per hour. That dense traffic represents the universe expanding normally, where the gravitational pull of all the mass in the universe constantly acts as a brake on the expansion of space.
A perfect analogy for the lambda CDM balance.
But suddenly, your specific lane clears out. You break through the pack, the heavy semi-trucks surrounding you vanish, and you find yourself in a massive, empty stretch of open road. With nothing boxing you in and no traffic dictating your speed, you naturally slam on the gas and accelerate to 80 miles per hour. You feel like you are moving much faster than the rest of the highway, but it is only because your immediate surroundings are totally empty.
This is precisely the physical mechanics of the void hypothesis. If our local cosmic neighborhood, the Milky Way galaxy, and the local group of galaxies surrounding us is actually situated deep inside a giant cosmic void, it drastically alters our local physics. A void is a massive region of space with a remarkably low density of matter compared to the universal average.
Less matter physically means less gravity.
Exactly. Gravity is the fundamental braking mechanism countering the expansion of the universe. If we happen to live in an immense bubble that contains significantly fewer galaxies, less gas, and critically less cold dark matter, there is simply less local gravity to pull inward. Without that gravitational anchor, the space immediately inside this void would literally expand outward faster than the space in denser regions of the universe.
So when our telescopes measure the Cepheid standard candles in the exploding supernovae right around us, they are objectively moving away 9% faster. Our local tape measure isn't broken. Our astronomers haven't made a mistake. They are accurately measuring a local anomaly. It is the equivalent of trying to calculate the average global temperature of the Earth by only using a thermometer mounted inside a running sauna. The instrument is giving you a perfectly accurate reading of its immediate environment, but a terribly distorted reading of the entire planet.
Which brings up the KBC void. Some astronomers have actively hypothesized the existence of a massive local underdensity known as the KBC void, named after Keenan, Barger, and Cowie, who proposed it in 2013. They suggested we might be sitting near the center of a roughly spherical region of space that is vastly larger and emptier than standard cosmological models predict.
If the void hypothesis is true, it is an incredible resolution to the crisis. We don't need to invent exotic new physics to fix the math. We don't have to throw away the lambda CDM model. We just have to accept that our neighborhood is weird.
But accepting that our neighborhood is weird violates one of the most sacred philosophical pillars of astronomy, the Copernican principle.
Explain the Copernican principle in this context, because I think this is where the physics bleeds into pure philosophy.
Ever since Nicholas Copernicus proved the Earth was not the center of the solar system, science has operated on the assumption that humanity does not occupy a special, privileged, or highly unusual place in the universe. We assume our vantage point is completely average. When we look out from the Milky Way, we assume the physics we observe locally applies uniformly to the rest of the cosmos.
But the void hypothesis violently shatters that assumption. It suggests that out of all the incredibly dense, bustling galactic superclusters we could have evolved in, we just so happen to spawn in the cosmic equivalent of a deserted cul-de-sac. Our view of the universe's expansion is artificially inflated purely because of our deeply unusual zip code.
It is a humbling realization. Our localized measurements of reality are perfectly precise, yet entirely unrepresentative of the cosmic whole.
It's an incredible synthesis of disciplines. Let's just step back and trace the arc of this journey. We started with a fundamental crisis, threatening modern astrophysics, 2 tape measures giving 2 wildly incompatible ages for reality itself, threatening a missing billion-year era of time. To solve this, astronomers didn't launch a bigger telescope to look further back in time. They looked closely at the ancient, low-metallicity subgiant stars caught in their volatile transitional phase right here in the Milky Way.
By understanding the delicate thermodynamics of a collapsing stellar core, they transformed these 155,000 subgiants into hyper-precise temporal checkpoints. They verified the existence of a hard cosmic floor, definitively proving the universe is roughly 13.8 billion years old, entirely vindicating the early universe microwave background measurements.
It proves that sometimes to understand the sheer vastness of the cosmos, we don't need to look billions of light years away. Sometimes the most profound answers are encoded in the chemical barcodes of the ancient relics floating right in our own backyard.
But solving one mystery has fully exposed another. The Hubble tension remains a reality of observation, but its fundamental nature has shifted. It is no longer an existential debate about the age of the universe. It is a debate about the recent structural behavior of our localized space.
Which leaves us with a truly lingering, almost unsettling thought. If this Hubble tension is indeed caused by our solar system existing in a massive cosmic void, a localized bubble of underdensity where the physical rules of expansion are slightly tweaked just for us, it means our immediate perspective on reality is fundamentally skewed simply by where we are standing. If our very mathematical measure of space and time is distorted because of the specific empty neighborhood we happen to occupy, what else about our human viewpoint, our scientific models, or our daily lives is completely distorted simply because we assume our local experience represents universal truth?